Okay, so in this video we're going to talk about the algorithm used to perform gradient descent. Last time we talked about gradient descent formulation. So let me quickly backtrack to see what was going on here. If you remember these diagrams here, just backtrack a little bit. So for instance, we had a case where we have an objective function, a cost function, and we have an initial starting point. Now this point on the curve represents that my initial value of theta 1 was down here, which gave a corresponding value of j theta 1 up here on the y-axis. And the fact that this is large, the fact that this slope is large and positive means that I want to take a relatively large step in the negative theta 1 direction. So here I get to this point here. So I actually achieve this point theta 1 here. Then I have a slope that's smaller but still positive, which indicates another step in the negative direction, and so on. Okay. So that's how we heuristically describe the algorithm. Right? So we go through this process. So we saw this in the last video. If you want more details, you can go to the previous video. So now we're going to mathematize that description. Right? So when the derivative is large, we want the step to be large. Okay? So the step is going to be proportional to the derivative. And in fact, the derivative, i.e. the slope, is in the opposite direction as the step. That's why we have the negative sign. Now, should the step actually be the negative derivative? Well, let's introduce a constant just to be safe. We can adjust this constant to match our conditions. And this constant is called the learning rate. And you'll see learning rate in many different contexts in machine learning. You find the learning rate also in deep learning. And in fact, the function of learning rate is identical to this function. It is adjust the rate at which you approach the best solution. Okay. So with no learning rate, well, this means no learning rate. Really means it means the learning rate is equal to 1. So if the learning rate is equal to 1, then we're just going to step according to the size of the derivative. And here you can see that here the size of the step. Don't look this way for the size of the step. The size of the step really is this way. This horizontal step is relatively large, and then this horizontal step is roughly the same. This horizontal step should be a little bit smaller than this one because the derivative is a little bit smaller. And then this horizontal step from this point to this point should be a little bit smaller, and this should be a little bit smaller as well. But the steps should be becoming smaller and smaller. I think that this diagram was just eyeballed, but you can see that as the parabola bottoms out, the steps become smaller and smaller. Okay? And in fact, a large number of steps were required to achieve the result. All right, so if we take a learning rate of 2.5, then you're multiplying each step by more. So you'll be taking larger steps at each case. The size of the first step with learning rate of 1 would be here. The size of learning rate with 2.5 is going to be 2.5 times as large. Okay? If I had learning rate 1, I would have this step. If I have learning rate 2.5, it's going to be 2.5 times larger. Okay? So we do the same thing, and here we get to the bottom point quite a bit faster. Okay? The question is, what learning rate should you use? What you really want to do is have an adaptable learning rate that will change as the progress of the algorithm takes place. All right, so here's an example of a much sharper function, and let's see what happens at this time when we use, well, here it says no learning rate, but we should think of this as learning rate equal to 1. And here's our formula. So what happens in this case, if we start at this point, so we're starting at this point on the x-axis here, and again, this is drawn schematically and possibly not to scale, but it's possible that since this is a large derivative and I take a step of this size, the step can be so large it brings me to the other side of the valley. And then here, it may do the same thing. So the steps are very, very large. Large back and forth like this. So this clearly is not a very good specification for a learning rate. Right? So you can see that the optimal learning rate is going to depend very much on the particular conditions of the problem. And just to show you how that works for this simple case, when you do have a quadratic function, y equals ax squared, so it would be a bowl-shaped, parabola shaped like this. Pardon my terrible drawing here. And if I start at the point xo, or x0, then my derivative, you know the derivative of a quadratic function has this form. Derivative of ax squared is 2ax. And if I use the formula with learning rate, I'm going to have x0, after one iteration, it will go to x0 minus alpha times the derivative, which is 2ax0, which can simplify to this value, x0 times 1 minus 2 alpha a. Okay? Now this alpha controls the steepness of the parabola. If alpha is big, it's a very steep parabola. If alpha is not steep, it's a much shallower parabola. Right? So you can see this behavior is very much depending on both alpha and a. Now a would be something that was part of the problem. A would be something that's given by the cost function, but alpha is something I can choose. Now you can see from this example that the choice of alpha will affect what happens. If I choose alpha less than 1 over 2a, then this 2 alpha a is less than 1. 1 minus 2 alpha a is positive. So x0 will, at the next step, be still a positive value. So x0 will come to some value maybe here. And the value of shrinkage is equal to the value of this constant here. So I can call this the shrinkage. So if alpha is less than 1 over 2a, x0 will go to perhaps this value x1. x1 will shrink by the same amount, x2, and so on. So in fact, it won't just take 15 times, it will take an infinite number of times, technically, to reach the 0 point. Maybe within machine precision, it will take 15 iterations. But technically, you never actually reach the point. Right? Now, if alpha is bigger than 1 over 2a, then this number 1 minus 2 alpha a is negative. So that means that x0 will jump to the other side. Okay? And we'll be jumping back and forth. So the sweet spot here is alpha equals 1 over 2a. Right? Now the problem is, in practical cases, you don't know what a is. But you can try to do your best to make an estimate for a. And we won't go into details about learning rate, but there is a lot of research that has been done on optimal choice of learning rate. So let's go back to our main discussion. Okay. All right, so in this case, it's clear that a learning rate of 1 was too big for this case where the function is really sharp. So we divide that by 4, and you can see that that's the step when alpha equals 1. If I make a learning rate of 1/4, the step is quite a bit smaller. And we're going to get pretty good convergence here. It goes to the function pretty quickly. Okay. So when the learning rate is too large, you're going to get jumping back and forth and slow convergence. But if the learning rate is really too large, you're actually going to do worse at each guess, right? So at a very sharp function and a learning rate that was over the top, then I would not get any closer. I'd get farther away. Right? Right. So now let's look at the case with 2 parameters. Well, the same thing we did with a single parameter theta 1, we can also do with theta 0. Okay. So we have the same equation for each parameter. Now, for those of you who know matrix algebra, which should be everybody, you can put these 2 equations into a single matrix equation. But we'll get there. You can see that the 2 equations do have the same form. the value minus the derivative. So the equations work something like this. If I start with theta 0, then I'll subtract this learning rate times the derivative and get a new value, which is called temp theta 0 here. Same thing with temp theta 1, updated from theta 1. And then I simply replace my original theta 0 and theta 1 with the new values. Now actually, you don't need these two steps. I could just say theta 0 equals theta 0 minus this value. The temp theta just kind of makes clear what's going on. You're doing an update and then restarting at that new value. This can be identified as the slope of j in the theta 0 direction. And this can be identified as the slope of j in the theta 1 direction. Because derivative means slope. And if you have a function of two variables, you're going to have slopes in two directions. Now I want to relate slope to this picture over here. First of all, let me explain why this picture here looks so different from this picture here. These two pictures are showing completely different things. This is showing our housing data, size versus price, and these are showing the two parameters of the fit for this data here. So this one says that as price increases, as size increases, price increases. This one here is saying that if I increase the y-intercept of my line fit, I need to decrease the slope to compensate. I discussed this in an earlier video, just to show you two examples here, just to make sure that we're on the same page. So if my theta 0, my y-intercept is here, I would need a fairly large slope to pass through the data. Okay, sorry, I don't have my tablet. So now if instead I have a y-intercept here, I would need a much shallower slope, which would to be a best fit. If I use the same slope with this y-intercept that I use with this y-intercept, I would have a very bad fit. So if you think about it, that's what this graph is showing, that given a particular value of theta 0, then as that value of theta 0 increases, the best value of slope will decrease. So just to emphasize, there are two parameters to adjust here. I can adjust both the theta 0 and the slope, so I can optimize by adjusting both. Now let me get back to the question that I started off this slide with. How does this picture show us about the slopes? Well, think about what these lines mean. If you think about this in terms of a topographic map, these lines are showing curves of constant height. So if this were a topographic map and I walked around one of these curves, I wouldn't be getting higher or lower. I'd be staying at the very same height. Right? Now if I have a valley here and I just walk around the rim of the valley, that's what this is showing. So if I'm on this rim of the valley, in what direction is downhill? Well, it's kind of toward the center, but in fact the direction of downhill is going to be perpendicular to the direction of constant slope. And that's a very important principle that carries over into several aspects of multivariable calculus. That the line of constant value of the function is perpendicular to the steepest descent and the steepest ascent. So if I was at this point here, then my steepest descent would be perpendicular to the blue line containing that point. It would not be directly towards the center of the valley. No, it's towards it's perpendicular to the line of constant slope. If I was at this point here, the steepest descent would be perpendicular. Now, in general, it's towards the point here, but it may not be exactly. If I was at this point over here, the steepest descent is perpendicular to the greenish line that this point is on. Now you can see that as you move, the direction of steepest descent is going to move. So the other aspect is that you can see here is how closely the curves are stacked together. You can see these curves here are very closely stacked together, whereas these are much more loosely stacked. What does that mean? If you think of these as altitude curves, 10 meters here. Well, here, let me go back to my arrow so you can see what I'm doing. So if we take these curves, for instance, this inner ellipse, maybe that's at a height of 10 meters. The second one's at the height of 20 meters. Third one is a height of 30 meters, and so on. So if I go in this direction, I go 10, 20, 30, 40, 50. I'm going up gradually. But if I go in this direction, I'm going 10, 20, 30, 40, 50, right? It's very steep here. So when the place where the curves are steeply stacked together, that means the slope is steep. And where the curves are more spread apart, that means the slope is more gradual. All right? So that's just a visual interpretation of this kind of contour plot that you should be aware of. Now, in this particular plot, the bluer colors are the smaller values of the function. So that's the convention in this plot. All right, so let's see how we can descend the cost down to the minimum. All right, so if I start here, as I mentioned, the direction of steepest descent is going to be perpendicular basically to this blue line. So it should be sort of in this direction. Okay. All right, so it kind of bent a little bit, but something like that. Now see, this one here also, the direction from here to here is basically perpendicular to this line of constant slope. Now, when I reach this point, the direction of steepest descent is going to be basically in this direction. Okay, you see how it turned there because the directions turn. And then here, from there on out, it's going to pretty much go directly in. Okay. Now, one thing I'd like to say is that this diagram is not really accurate, excuse me, because here this slope is very gradual. So the steps that you took here would not be so large, they'd be small. Because we know that the steeper the slope, the larger the step. Right? So that's the way that that's the way the steepest descent works. So in fact, if we did use this algorithm here, it would take quite a long time to reach the point here. I said steepest descent. Sometimes people say steepest descent. Steepest descent and gradient descent are synonymous. All right. So here's the general description of gradient descent, including the loop structure. So if you define your cost function, J, which would be a function in Python, which depends on n parameters, which in Python would be an array of values. Then you'd create these temporary variables for each of the different parameters. So temp theta 0 equals temp theta 0 minus this step, which includes the learning rate and the derivative. So here we're basically just doing an update for all n of the parameters involved in this function. But each one has the same structure as a single parameter optimization. Right? Then once you do this, then you can update and you basically reset your parameters to the new values. Now, again, I made the point before that in Python, you really don't need these two steps. I could just have here, instead of just doing the temp here, I could just say theta 0 equals theta 0 minus this. Theta j equals theta j minus this. And then I wouldn't even need this step. And we'll do even better than this. We'll express all of these equations as a single vector, and you'll see that shortly. All right, So we've introduced gradient descent, or what I called steepest descent. And in the next video, we'll apply this to linear regression and see how it works. I will say in advance that gradient descent is not the only way to do linear regression, but we're using linear regression to introduce this concept. That's why we're spending time doing it this way. All right, thanks for watching.